Hello to everyone and welcome to this session of the 2021 American Control Conference, in which I present the paper entitled Modeling Control and Stability Analysis of Flexible Rotating Beams Impact During Contact Scenario. The principal objective of this paper is to find the solution properties of the model of a controlled rotating flexible beam that enters in contact with an external environment. So, in this presentation, we will first introduce the framework of switching semilinear operator systems. Then we will find the model of the external environment, following by finding the model of a rotating flexible beam that enters in contact with this external environment. And finally, we will determine the infinite time behavior of the solution of the closed loop system with a proportional derivative controller. We consider in the following switching semilinear equation, where we consider an hybrid state composed by a continuum state X belonging to a state space capital X and a discrete state M that belongs to a discrete space capital M that is defined as an interval of the set of natural numbers. Then we consider AM linear operators that are associated to a certain discrete state that are defined on a common domain, such to avoid some problems during the switching times. We consider FM as nonlinear mappings associated to a certain discrete state that maps from the state space to itself. And finally, a discrete transition function, eta, that give us the discrete state that is active in a certain instant of time. First of all, we divide the state space in n different subspaces, such that the union of all the different subspaces give us the complete state space. Then we allow only one vector field to be active in a certain subspace, and therefore we are implicitly assuming that our discrete transition function give us the active discrete state in a certain instant of time, dependingly on the position of our state inside the state space, and in particular if it belongs to a certain subspace or another one. Then we associate to each subspace a certain Lyapunov functional, and to a certain function to be considered a Lyapunov functional, it first of all have to map from the state space to the right-hand part of the real numbers, and first of all it must be radarly unbounded. That means that if the norm of the states goes to infinite, also the functional have to go to infinite, and secondly, the time derivative along solution of this Lyapunov functional must be non-positive for all the states belonging to the same subspace to which this Lyapunov functional is associated to. But how to compute the Lyapunov functional derivative? In each subspace, the time derivative corresponds to the multiplication between the Frechet derivative of the Lyapunov functional with the vector field associated to the same subspace to which the Lyapunov functional is associated to, and must be non-positive. And in the time derivative in another subspace, it's also possible to compute it and can be computed exactly in the same way. But we don't have any restriction on the non-positivity of this time derivative. Then we can introduce the theorem about boundedness of solution, and we assume first that there exists a unique local mild solution for the dynamical switching semilinear equation that we considered before. Then, if there exists a Lyapunov functional Vm for every vector field that compose our switching semilinear operator system that satisfy a certain switching in condition, that means that this Lyapunov functional has to be non-increasing in their switching, in their activation time, then our our system possesses a globally bounded mild solution for every initial condition in the state space. But what does this switching in condition means? In the left picture, you can see a Lyapunov functional that is non-increasing along its activation time, but the second time that it becomes active, its value is greater than the first time that it becomes active, and therefore it does not fulfill the switching in condition. In the right picture, instead, you can see a Lyapunov function that does fulfill the switching in condition. We can now pass to the modeling of the external environment. In particular, in a paper of 1975, the author Kenneth Hunt proposed to model the impact of an object with an external environment with a force that is zero in non-contact times, and it is equal to the parallel between a nonlinear spring that depends on the nth power of the deformation of the external environment and a nonlinear damper that its coefficient depends also on the nth power of the deformation of the environment. And in this paper we consider the case in which n is equal to 1. Then we define the function eta that distinguishes between the contact and non-contact scenario. In particular, eta is equal to 1 in contact, means that the distance between the object and environment is positive, and it is considered equal to 0 when the distance is negative. And what does it happen in the case in which the distance is equal to 0? We distinguish the case in which the velocity point towards the environment, and we consider this case to be a contact case, and in the case the distance is equal to 0 and the velocity points away from the environment, the object is considered not in contact with the external environment. Then the Porte-Hamiltonian model of the rotating flexible beam that enters in contact with the external environment is composed by the power-preserving interconnection of a finite-dimensional Porte-Hamiltonian system with an infinite-dimensional Porte-Hamiltonian system. In particular, we remarked that the impact force only affect the finite-dimensional dynamic, as well as the input only affect the finite-dimensional dynamic. In particular, we make the assumption, the Timoshenko beam assumption for the distributed parameter part of our system, and therefore the states is composed by the linear and angular momenta and the shear and angular deformations. Then, for the lumped parameter part of our system, we observe that the states P1, P3, Q1 and Q3 corresponds to the angular momenta and angular displacement of the inertia of the motor at the x equal to 0 side of the beam, and of the load at the x equal to L side of the beam. And in particular, we want to remark the state P2 and Q2 that corresponds to the momenta, the linear momenta of the load at the x equal to L side of the beam, and of the linear distance between the load and the environment, and therefore it will be this variable that gives us the condition if the load is or not in contact with the external environment. Then we apply a proportional derivative control, where we assume that the parameter Q1 naught is positive, such to have our equilibrium position in contact, and we make a change of variable with respect to the equilibrium point. Then we explicit the discrete transition function eta such to define two different semilinear equations. One linear equation corresponding to a non-contact scenario, and one semilinear equation corresponding to the contact scenario. Then we define the Lyapunov functional associated to each vector field that compose our switching system, and we set the non-contact Lyapunov functional to be equal to the non-contact closed-loop energy of our system, and the contact Lyapunov functional to be equal to the contact closed-loop energy of our system. In the left picture, we can see the Lyapunov functional in the whole time interval domain, while in the right picture we can see the simulation of our Lyapunov functional only in their activation time, and we can appreciate that these Lyapunov functional are non-increasing along the system solution in their activation time, and moreover that they fulfill the switching in condition such that we can possibly use the bounded solution theorem that we presented at the first part, in the first part of the presentation. So in this paper we presented first a theorem about the boundedness of solutions of switching semilinear equation. Then we presented the Porte-Hamiltonian ODE-PDA model of a flexible beam that enters in contact with an external environment. And finally, we studied the stability of the closed-loop solution with the help of numerical simulations. In the future research, we will first focus on formally proving the existence of solution and the boundedness of trajectory of defined closed-loop systems, and therefore we will also focus and study the asymptotic stability of the same closed-loop system. The presentation is over. Thanks for your attention.